Let's start this. So, let's see here. It's March 4th, but I'm living like it's the end of the term already. I'm like, oh yeah, March is basically done. April doesn't count. Oh yeah, it's basically summer already. So here we go. Chapter 5. How I'm going to do this is just chapter 5, part 1, part 2, etc. Okay. Great. So make sure you get your assignment in. Assignment 4. Bit of a doozy on the back, right? But I'm sure you gave it a shot. Here, I'll give you this. No. Well, not more work, more information. Okay, so everyone got a chapter 5 printout. She's a big one. 21 pages. Did I feel bad printing it? Yes, I did. So please use it. Did I spend all weekend making it? Yes, I did. Please use it. Anyways, whatever you can do to use it is great. Basically, any question that you will have, be it for studying, for homework, for assignments, for whatever, the answers are in here. I can guarantee it. Because I've basically purged everything that I can possibly tell you, into these pages. So it's in there. It's just a little bit hard to read all those. So tight. Anyways, so handed in assignment 4. The reason I kind of did a fire drill on assignment 4, usually I give you a week, right? Wednesday to Monday, not really fair. Well, sort of. It's not unfair. Was because I wanted you guys to practice, especially hypothesis testing and confidence intervals with chapter 4 stuff, because we're going to keep doing the same stuff in chapter 5, okay, and chapter 6. So we need to know this stuff, and the more we see it, the more easily it'll come to us, right, when we read these questions and try to figure it out. The biggest problem that we're going to have on test 2, for example, is you'll have all these questions and you'll have to figure out what type of question it is. So far it was fine. We've only seen one type of question. Okay. Today I'm going to introduce the second type of question. Thank you. Oh, here. Oh, look at you go. It's 21 pages. And so as we go through, we're going to be introducing these new types of problems. And it just depends on what information are we given in the question. That will determine what type of question we have. Just like in real life when we're collecting data, how we've collected that data and what it's giving us, that's going to dictate the type of question that we have. Right. So far, we've only looked at where we've collected one sample, and we want to analyze the mean of that sample and compare it to some value. Right? For example, on assignment 4, you had your sample mean price that you wanted to compare to 339,100. Right? Has it increased or has it not increased? Right? So that's how we deal with one sample. We have sample information and then a value we want to compare it to. Okay? Now, the difference between chapter 4 and chapter 5 is in chapter 4, we started and we said, okay, we're going to pretend to know sigma, but I already kind of gave you a preview of that's not really going to be the case in real life. Remember, sigma is So just looking at these formulas, we've looked at these before, right? And we've said, besides the name of them, of course, if they're calculating different things, they have to have different names, right? But besides the names of them, the only difference here is that here I've got sigma, and here I've got S, which is your sample standard deviation. And so the only difference between doing a Z calculation and a T calculation is that here in T, you're not assuming that you know anything about the population, so you're going to use the sample standard deviation instead. Right? And so for differentiating these types of questions, they're actually going to look the same, right? The question is just going to be, where did the standard deviation come from? So it's not if you know the standard deviation or you don't know the standard deviation, I'll always give you a standard deviation. It's just, where did that standard deviation come from, right? Here, remember, Greek letters are from the population, right? So sigma is the population standard deviation. So if I say, and I have some examples on here, if I say things like, blah, blah, blah follows a normal distribution with a mean of this and a standard deviation of this, then you can assume that you know sigma. Or I might even say, assume the standard deviation for all manatees is whatever, 4, right? Then we're assuming that we know sigma. Okay? For sigma unknown, okay, will be much more common, right? Because that's going to be where I tell you, okay, you've collected the sample, collected a sample of 50 manatees, and you found the mean to be 12 and the standard deviation to be 2, right? So here I'm giving you information from the sample. And just as a heads up, I actually mucked up on the assignment. This is actually a sigma unknown question. I was safe though, because you guys hadn't seen that before, so it wouldn't be confusing. But if you're going back to it, I screwed up, okay? You did it right if you assumed that you knew sigma. Or if you picked up on that you didn't know sigma and you used S, that's even better, but not something that I'm expecting to see. Okay? So, but in general, it'll be something like, assume the standard deviation of all house prices is 94,000 or something like that. And so now, the question will just say you took a sample of this and you found the mean and the standard deviation. So that's implying that the mean and the standard deviation are both just from the sample, right? So do I have any margin notes here? No. In real life, you'll never do a Z calculation, okay? The reason we start with Zs, bless you, is because what we talked about before was that there's variability in the sample mean, right? Because if we think about, we collect a sample and we find the mean, and then we collect a different sample, even though they're all randomly selected and these are well collected samples, the mean, the sample means are gonna be different depending on the sample, right? And so that means that we have variation in our sample mean. We were able to deal with that here in the Z situation, but now we have variability in X bar, but we also have variability in the sample standard deviation, right? Because the sample standard deviation is now also going to change depending on our sample, right? So we have this kind of like, how's it go? I can never do it. You can't do it. You have to rub your belly and pat your head. We've got these two things that we have to keep track of, right? And so that's why we start here, because it's nice and stable. It's just Z, right? Here, we've got two things that are varying. And so we need to take that into account. And that's what the T distribution does. So, in real life, we're just going to be calculating T's. So if you're reading research, for example, so papers, whatever, articles, they'll often say that we did a t-test of this type, right? And so in this chapter, we're going to go through 3 types of t-tests, the 3 most common t-tests. Can't think of any others. I think there's only 3 t-tests. I don't know. Don't hold me to it. Can't think of any more right now. But just some common t-tests that we can do. Okay? And so in real life, we use the t-distribution. Here's where I outline the assumptions, really wordy stuff. But at the end of the day, for t's, what we're going to end up doing is we're just going to use a t-test anyways. We're going to check the assumptions, but not really, because we don't have any other options. And so if you collected information and you have to analyze the mean, there's really nothing else that you can do besides mention maybe, oh, it doesn't look like it follows a normal distribution. Oops, still going to use a t-test, but keeping that in mind, right? And so we've got all these assumptions, but for t-tests, it's not going to be that important. It's not going to be something that I emphasize, you checking the assumptions. Later on in chapter 6, when we move to proportions, then I'll emphasize the checking the assumptions. So then we'll be checking the assumptions. But for t's, no, we're not going to check the assumptions. But I'll run you through them just so you've heard them. But it's not something that I'll get you to do on a test. Okay. So some things that say that we can use a t-distribution are that, okay, all your observations in your sample have to be independent. Okay. Independent meaning that, you don't have an observation that hinges on another observation, right? What are you going to answer? What are you going to answer? Right? That kind of thing. And so you get independent samples by doing random sampling. And also, so you've collected a random sample, that's basically all you can do. And that's what we established in chapter 1, right? Whatever we do, wherever we go, all we have to do is collect a random sample, and that's the best thing that we can do, right? And so a random sample is gonna clear a lot of these assumptions. Okay? But another thing that we have to sort of keep in mind is that, because we keep hearing, okay, we want big sample sizes, huge sample sizes, we want these large sample sizes, but also there's kind of a cap on that, because we don't want our sample sizes to be too large. And I call this kind of a bogus assumption that our population should be at least 20 times as large, because if you're lucky enough to have a large sample size, I say take it and run with it, okay? Probably never gonna happen, so it's not really an issue. But just to keep it in mind, the reason you don't want to have too much of the population in your sample is because inevitably you're going to have non-independent observations, right? If you've collected too much of your population, you're going to have siblings in there, you're going to have people from the same cities, depending on, the scope of your study, right? And so you're going to have non-independent observations, whereas if you've got a small sample, you're less likely to have non-independent observations. And that's the only reason. Then from here, 3 onwards, all I'm basically saying is, as long as you have a large enough sample, so a sample size larger than 30, let's say, you can assume that the assumptions for a t-distribution are satisfied, right? Just by the central limit theorem. If you have a smaller sample size, what you should do is you should make sure that your sample looks approximately normal, or at least single mode, right? So just one peak and roughly symmetric is good enough. Okay? And so here, on the side, what I'm going to write is, make it a little bit smaller, 3 onwards. Whoop. And then on the side here, just because I don't have the same page that you have, well, I do, but I have to scroll over. So to satisfy the assumptions for inference, we must have a sample larger than 30. Yeah, look. Oh, and I was so bummed. Was it last Monday, last Wednesday? I only found out it was pink shirt day when I was driving to work. So I'm rocking the pink shirt day today. By myself, but still. Because I have this perfect shirt. So our sample size has to be larger than 30. Get that in the notes. No. It's important. Emily is anti-bullying. Great. So we have to have a sample size larger than 30. That's not always going to be the case, right? And so if our sample is smaller than 30, check the distribution. What I mean by that is make a histogram of it. Make a histogram of it to make sure it's unimodal, so just one peak, and symmetric. Right? We've been calling that normal, but if you think about, so unimodal, so one peak, and symmetric is a little bit more flexible, right? Because then it doesn't even have to slope down necessarily towards the end, right? As long as it's symmetric about some sort of peak, then you're satisfied, right? And make a histogram of it, and make sure it looks unimodal and roughly symmetric. So I've got this huge blurb about the assumptions and stuff, but like I said, it's not something that I'm expecting to see on a test. On a test for this stuff, we're going to be doing hypothesis testing and we're going to do confidence intervals. Nothing in between, or very little in between. But here's what's going on in the background that you should be checking if you're doing a research paper or something like that. Any questions about that? So the t-distribution is very similar to the z-distribution. The z-distribution is the normal distribution. Same type of shape, centered on 0. Notice that the only difference really is, so here on the dotted line, we've got our z that we're used to seeing. The z closes in on the axes pretty quickly, right? Goes up and then plunks down on the axes pretty quickly. Whereas t has more space in the tails, right? So it's kind of lifted off in the tails. One thing is that no matter what the shape of the curve is, the total area under the curve is still 1, right? And so for them to have the same area under the curve, right, what happens is to make room for gets pushed down a little bit in the center, right? And so you've got this normal Z distribution here, and then the T kind of goes like this, right? What does it mean to have thicker tails? Well, the area under the curve, remember, is the probability, right? Now that you've got more area further out into the tails, what it's just saying is, I'm just going to leave room for these little bit more extreme observations, right? And so, and the reason for that is, if we've collected small sample sizes, the T distribution makes more room in the tails, just because it's saying, well, based on this small of a sample size, I don't know, I can't tell you for certain if this is extreme or not until it's really, really extreme, right? And so these thicker tails, right, just make room for a little bit more extreme observations. And what we'll see when we compare the two is that we don't actually need a huge sample size for them to be essentially the same. Okay? In fact, here, if you go down to the next one, I guess I should talk about degrees of freedom first. Degrees of freedom are how we communicate our sample size to our T distribution. Okay? So for the one sample case, our degrees of freedom are going to be your sample size minus 1. So just n minus 1. And if you have a look at your formula sheet, you'll see that I give you the degrees of freedom for each of the T's that we'll calculate, right? So the degrees of freedom for one sample is just your sample size minus 1. Right? And so that's how it knows, okay, that's how many degrees of freedom I have, and that's essentially telling it what your sample size is. Right? And then from there, as your sample size increases, your degrees of freedom will increase as well. Right? As your sample size increases, so you've got here huge, small sample sizes, you've got a T that looks like this. As your sample size increases, your T is going to get smushed down, and it's going to approach the Z curve. Right? And what we see here is, if we have a degree of freedom of 1, we have a sample size of 2, right? Because our degrees of freedom is your sample size minus 1. Right, so here we're looking at a sample size of 2. That's the faintest line. I know it didn't print that great. It's all great, but sure. And so that one is going to be the one with the thickest tails. Right? But even if you look and you go to 10 degrees of freedom, that's only a sample size of 11. Right? And now they're basically the same. Right? Here's your Z. Here's your 10 degrees of freedom, right? So even at 11, a sample size of 11, it's basically behaving like a Z distribution already, right? It's just a technicality that we have to use the T versus the Z. So, any questions about that? No. Yeah. So, your degrees of freedom communicate to the T distribution what shape to take, right? Basically, how much room to leave in the tails. Okay. I've done this a lot today. But that's how it behaves. So what I've done, how I've laid out these notes is, in the first part of chapter 5, I just introduce the T's, the T table, how do we use it to find p-values, to find critical values, right? Because we introduced those in chapter 4. Right? And so now I'm just saying, okay, well, now that we have T's, this is how we do it for T's. Right? And then I'll introduce the different types. And as we go along, I'm just going to say, okay, for this scenario, only this changes. And what you'll notice is that very little changes as we go through these types of problems. So first, let's talk about using the T table to find p-values, right? So in hypothesis testing, if you have calculated a t, then you have to use the t-table to find the p-values. Yikes, right? All these little things that we have to keep track of. Okay. So let's have a look at our t-table. Where are my tables? Here. So here's my t-table. And we've used this table before, right? We've used this table to find our critical values. So the Z star for the confidence interval, right, for Z. Because what we did was we said, okay, we have, I'm just gonna do this. How about that? How clever. Took me way too long to think of, but that's okay. If we want a 95% confidence interval, right, then what we do is we just scroll down, and we found a Z star of 1.96, right? And that's what we use in our confidence interval. Now, what we said then was, well, just ignore all of this. Now we can't ignore all of it anymore, right? But it doesn't look that bad, right? We've got our degrees of freedom out here, right? And so your sample size is never going to change, right? You've collected a sample of 30 people, found your sample size, right, 30, and then your degrees of freedom is 30 minus 1, 29. But once you have your degrees of freedom, 29, for example, then you can ignore everything else in the table. Right? Just because 28, well, that's a different sample size, so that doesn't matter. And then 30, that's a different sample size, so that doesn't matter. So because your sample size won't change, you're only going to be looking at this 29 degrees of freedom row. What I do, because it's hard to read these things and you don't want to be jumping around, is just in the test, or if you're working on an assignment, just take a piece of paper and just kind of follow it along. You'll try to be a hero here. Those little buggers jump around. No, my finger tends to go like this. Anyways. So, for the t-table, we have to know our degrees of freedom. Right? We said for one sample, then our degrees of freedom is our sample size minus 1. Fair enough. It's actually not going to change that much. Even if we have 2 samples that we're going to be comparing, which we'll do in the last section of chapter 5, it's going to be the smallest sample size minus 1. That's your degrees of freedom. Right? So things don't change dramatically. What's going on here is that for each of these degrees of freedom, I'm just going to look at the 20 just because it has the little shaded area and I don't want to be floating around. We have 20 degrees of freedom. What it's doing is it's giving little cutoff values of t. So it's just doing little check-in points, moving out from 0, moving out further and further into the tail. How it's picking those values is from up anymore, so you can see down here. Here, we've got our one-sided p and our two-sided p. We already know about the one-sided p-value and our two-sided p-value. I'll only focus on the one-sided p-value just because the two-sided p-value is just the one-sided p-value times 2. You can check it, but 0.25 times 2 is 0.5, blah, blah, blah. Okay. So I'm just going to talk about the one-sided p. Remember, the one-sided p is the area in the tail, right? And so what this table does is it's saying, okay, if the area in the tail is fixed to be 0.25, what value of t at 20 degrees of freedom makes that happen? 0.687. Right? Then it goes on to say, okay, well, if the area in the tail is 0.2, what t makes that happen? At 20 degrees of freedom, 0.860 makes that happen, et cetera, et cetera. So it's just moving further and further out into the tail until it kind of taps out here with an area in the tail of 0.0005, they said, well, why would you possibly want to know anything beyond that? You can just say that the area past here, right, is less than 0.0005. Right. So I know you encountered that on your assignment, right? You got a Z of 6.16. What on earth are we supposed to do with that? What we said was, okay, well, 6.16, it's unlikely, right? Assuming the null hypothesis is true. It's not impossible though, because we have to keep in mind that these tails keep going from negative infinity to positive infinity, right? So when we find these huge Z scores or T scores, what we're just finding is the probability that the null hypothesis is true is really small, right? Because the area in the tail that far out is going to be really small, right? And so same thing happens here. Once you have a T greater than, notice how it doesn't really change, 3.89-ish, right? Then they're saying, okay, the area in the tail is less than 0.0005. Right, and that's all you need to know. Same thing on this side. T starts at 0, moves out. And so they haven't given you values between 0 and 0.687 or 20 degrees of freedom, just because who cares about that area? Right? Between 0 and 0.25, there's 0.25 in between there. But you can still find the probability of something smaller, so closer to 0 than this, for example. Right? It's just larger than 0.25. So you can still go beyond the tables, and I've got a note of that in the notes, in the margin there. Because it will happen again, where we find these huge Z's and T's when we're calculating them. But really all that's telling us is that, okay, we're most likely going to be rejecting the null hypothesis. And that's all it's saying. Notice that we only have positive values here. Right? And so our T can take on negative and positive values, just like Z. Right? But because it's symmetric, whoever made the table decided, well, you only need one side. And then you'll know what's going on the other side as well, right? So once you calculate your T, what we do is we take the absolute value of it. And I think most of you have worked with the absolute value before, but if not, it just means you drop the negative, right? And we show it by putting these two vertical lines around the value to say, oh, the absolute value of -2 is just 2. Okay? And I'll show you how to denote that in your answers. Last thing that I can kind of think of off the top of my head is, as long as you have your degrees of freedom and you found them and they're here, so you have 17 degrees of freedom, 17, that's great. What if you have a sample size of 64? 64 minus 1 means we have 63 degrees of freedom. So then we go here, and we're looking, right? We have options of 60 and 80. What we have to do, and this is important, we have to round down to 60. Because if we went to 80, now in that example, we probably wouldn't be inclined to go to 80, right? But let's say we had 79 degrees of freedom, right? In that situation, you might be inclined to go to 80. But 80 degrees of freedom is saying that you have a sample size of 81, which you don't have. Right? And so if you're rounding up here, you're saying you have a larger sample size than you actually do, and that's not good. Right? And so what we always do is we have to round down to the nearest degrees of freedom if we can't find it on the table. Okay? Even when it hurts, for some weird reason, it hurts a little bit. Because let's say you collected a sample size of 995 So good, right? Huge sample sizes, 995. You have 994 degrees of freedom. You're rich with degrees of freedom. But then you come to the table and you've got options of 100 and 1,000. And for some weird reason, it just hurts a little bit when I have to round down to 100. But that's what I have to do, right? Because 1,000 is assuming that I have a sample size of 1,001, which I don't have. I only have 995. Right, and so regardless, you have to always round down to the nearest degrees of freedom on your table. Good, good, good. Any questions about the t-table? So it's different than the z-table, but I think once you get used to using it, you'll find it's more efficient than the z-table. Right? But we have to use it first, so give it some time. So like I said, everything that I just blabbed at you is on page 3. All these little ins and outs of using the t-table, they're all on page 3. Here I've outlined what to do if your t-value is off the table, right, in margin here. Oh, the one thing I forgot was for our t's, we have to have 3 decimal places for our t that we calculated, right? So we have to have at least 3 decimal places, which is different from z, right? Z, we had to have exactly 2 decimal places because that's what our table was using, right? It had to have 2 decimal places. Now, the t, we have to have 3 decimal places, or at least 3 decimal places. We can handle more now, but we have to have at least 3 decimal places, and that's just to match the t-table, right? So our number of decimal places is just dictated by the table that we're using. Okay. So, and I had that here. I'll highlight it. I put it over in the margin, but these are actually important notes, all of them. But I'm not going to highlight all of them because it wouldn't make sense. So, how we're going to use the table, right? Because the whole goal of using the table is to find the p-values, right? And so if we go back to our tables, in our hypothesis testing, right? First step is set up our null and alternative hypothesis, right? Second step is do the test, and this is where we're going to calculate a t-value, right? Regardless of the type of question that we're talking about in chapter 5, we're always going to calculate a t. Right? Third step is find the p-value. Right? Finding the p-value involves a table, and so first thing you're going to do is find your degrees of freedom. For one sample, it's just your sample size minus 1. Then you're going to take your, and I just kind of imagine grabbing it from my calculations above in step 2, and then I just have to figure out which values. So let's say, just because it's right here, I have 15 degrees of freedom, so a sample size of 16, right? And let's say I've calculated a t of 2, just flat 2, okay, 2.000. So I've got my 2.00 that I've calculated. What I'm doing is I'm just going to go through here and notice that these are just increasing as I move along. Right. 2 would fall in between 1.753 and 2.131. Right. So you're going to find 2 values that wrap, or the 2 values that wrap around your calculated t. Okay. Then you're going to jot those down. We'll do that in the example, but you're going to jot those down. And then what you're going to do is to find your p-value, you're going to roll down to the bottom. Where was I? 15 degrees of freedom in our made up example. somewhere between here and here, 1.753 and 2.131. Our one-sided p-value, if that's what we wanted, is, oh, I lost it, between 0.025 and 0.05. Notice that these p-values, right, they're decreasing as we move out this way, right? Because we're moving further and further out into the tail, right? So the area is getting smaller and smaller and smaller. So one thing to keep in mind when you read these p-values is you have to read them from right to left, because we always report intervals from the smallest to the largest. Right? No interval exists between 0.05 and 0.025. You can start at 0.05, go to 0.025. And so you have to read these from right to left, but that's the only tricky part. So what's nice about the t-table is that it just gives you the p-values, right? And one thing that's going to take some getting used to is that before with the z-table, we just had a value for our p-value, right? Now, all we're able to say is that it's somewhere between 0.025 and 0.05. Right? Somewhere in here is our p-value. We can still use this range to compare it to the alpha level, right? Remember, we have to have a p-value less than the alpha level to reject the null hypothesis, right? And so the default alpha level is 0.05. And so is this value that's somewhere between 0.025 and 0.05, is it going to be less than 0.05? It is, right? Because we're saying at the very largest that it could possibly be is 0.05, right? And so from this range, even though it seems a little bit less precise than what we're used to, right? We can still say that, well, because our p-value is somewhere between 0.025 and 0.05, it's less than 0.05, which means we can reject the null hypothesis. Okay? So we can still draw our conclusion based off of this interval. Bless you. I'll never give you an interval for the p-value where the alpha level is somewhere in there. That's not going to happen, so that's not something to worry about. Okay. Any questions about that? Yeah.
It's always larger than the opposite ways.
Yeah, so we use the alpha level of 0.05 as the default. Is that what you mean?
Yeah.
Sort of. Sort of. It depends. So we'll see some examples. Yeah, where it's above. But we'll see. Okay. Cool. And then of course, if we use R, it'll give us the actual p-value. So it's not just going to give us a range anymore. But for doing things by hand, all we need is a range of these values to get a good grip of whether we can reject the null hypothesis or not. All right. Oh yeah, I always forget this one. So the critical value. The critical value, remember, is that it was the Z star for our confidence interval. Now we're going to need a T star without even knowing what the confidence interval formula looks like. I'm just going to tell you that you need a T star. And how you find it is basically the same as before. So if you want to make a 95% confidence interval and you have to find the Z star, right? What did we do? We had to find 95 here, and then we had to scroll down, and our Z star was 1.96. Right? The difference now to find a T star is you start in the same spot, 95% for a 95% confidence interval, and then you just go to your degrees of freedom. Right? So instead of going all the way to Z star, you just stop at your degrees of freedom line. Right? So you still have to know your degrees of freedom for confidence intervals, and that's where you're going to find your critical value. All right. Da, 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 da. Are you ready to talk about a question type? Yeah. So as far as naming the types of questions that we've seen, so far we've seen one sample mean sigma known, right, because we knew sigma. Now we're going to talk about one sample mean sigma unknown, right, meaning our standard deviation is from the sample. So one sample means with a t-distribution is really just one sample mean sigma unknown. And how these questions are going to go, or how these notes are going to go, is I introduce a question type, and then we do hypothesis testing. I tell you everything you need to know about hypothesis testing, 2 examples, confidence intervals, 2 examples, on to the next type. So it'll have the same setup for all these types of questions. Okay? We're just going to work through them. Okay. So hypothesis testing is a beast, right? There's a lot of steps, a lot of ins and outs that we have to keep track of. And what you'll find as we do more and more of them is that they'll come more naturally, right? You have to have your null hypothesis and your alternative hypothesis. What's nice about just having a one sample means problem, right? If you read the question, you say, okay, well, it's definitely one sample. And then you can decide if you have sigma known or unknown. But regardless of what it looks like, your null and alternative hypothesis is going to be the same, right? Because you still have a sample mean that you want to compare to some value, right? And that value is going to be your mu sub 0, your mu naught. Okay? So nothing's changed here. We're still hypothesizing about what the population mean might be. So that's nice. So that stayed the same. Great. In step 2, do the test, do the do. We have to calculate a test statistic. It's hard to say. Fun to do. We calculate t, x bar minus mu. Oh, I have a little, I forgot to put the mu sub 0 on here. It's actually not critical. Mostly because you could just have mu here, remembering that we do all our testing assuming the null hypothesis is true. The null hypothesis is saying that mu is mu sub 0. So it's not too bad, but on the formula sheet I have mu sub 0. So that's what you have. Okay. So x bar is your sample mean. Mu sub 0 is your hypothesized mean. Right? We want to know how far is your sample mean from the hypothesized mean. And then you've got your sample standard deviation over the square root of the sample size. So in terms of the actual calculation, nothing's changed from a z to a t. It's just the information that we're putting in there is a little bit different. Step 3. You find the p-value, right? And like we just said, we're going to use the t-table, and for one sample mean sigma unknown, we use degrees of freedom is n minus 1. And that's on your formula sheet. Then, once you have your p-value, then you can state your conclusion, right? Draw your conclusion. And just to re-emphasize what those conclusions are, because there's only 2 possible conclusions that you could make, right? First one, if the p-value is less than the alpha level, right, then we have enough evidence to reject H0 in favor of HA. Or if the p-value is not less than the alpha level, then we do not have enough evidence to reject H0. It's simple as that. Those are your only 2 possible conclusions that you could draw. Notice that I'm only talking about H0 and H0. Can I reject H0? Can I not reject H0? Yeah. And I've got these conclusions in here. They're from chapter 4, so we've seen these before, but it's just nice to have them in the same package. notice that here is less than. We have enough evidence. If it is not less than, we do not have enough evidence. So that's why I've chosen that sentence structure. It's because they kind of match. Right. So it's not until you have a p-value that's small enough, meaning you've moved out far enough into the tail, then you can reject the null hypothesis in favor of the alternative hypothesis if it comes to that. See if I have any margin notes. Nope. Any questions before we do our example? All right, you got it. So what I've done, let's have a look at this page first. Like I said, there's 2 examples for each little thing that we go through. Okay. The first one is I've typed out all the solutions, but because I talk around and make little side notes about things that I'm doing as I'm solving the problem, what I've decided to do is that everything that you need to show on a test, for example, for full marks, is in a box like this. Okay? So the core material that you need to tell me is all in boxes like that. Right? Everything else, I'm just kind of making little notes to, I don't know, fill you in on little pieces of information as I go. Right? So, and then the next example, we'll just do together by hand for practice. So, the level of dissolved oxygen in a stream or river is an important indicator of the water's ability to support aquatic life. It sounds important. A researcher measures the dissolved oxygen level at 15 randomly chosen locations along a stream. Here are the results in milligrams per liter. And so we've got a stream that we're concerned about. So we've got these 15 randomly chosen locations. Right, we have a sample size of 15. And we found these measurements. And then we calculated the mean and the standard deviation of these measurements. Fair enough. So that's our sample information. A dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk, right? So that's not good. So basically what we're checking is, okay, we have to check in to make sure that the dissolved oxygen level is not less than 5, right? I can imagine a lot of, power plants and stuff have to check things like this in the rivers that are close to them just to make sure that things are still tickety-boo. Pretty reasonable example, right? And so dissolved oxygen level below 5, that's not good. Is there evidence that the aquatic life is at risk at the alpha equals 0.05 level? Okay. So even though I'm not going to say do a hypothesis test, right? Whenever I say is there evidence of something, you have to do a full hypothesis test. Another clue is it's going to be worth a lot of marks, between 7 and 10 marks-ish, right? So it's going to be kind of a big mark question. And that's how you know you have to do a full hypothesis test. Because just reading this here, is there evidence that the aquatic life is at risk? Doesn't seem like that big of a question, but what we'll find is that it is. 4.771 is less than 5, right? That's established, but that's just our sample, right? And so we're going to use this information to say, well, is 4.771, is it significantly less than 5? Because then we have a problem. So the value that we want to compare our sample to is 5, right? We want to compare our sample mean to 5. Is it less than 5 specifically? So in our hypothesis, our null hypothesis is that mu, in this is the population mean for the entire stream, right? So the whole stream population mean is equal to 5, right? First, we have to assume that the dissolved oxygen level is 5, and then once we've collected our sample, maybe we'll find that mu is actually less than 5. Right? But we have to assume it's 5 until we have proof otherwise. So our alternative hypothesis is that mu is less than 5 because that's what we're concerned about. Right? If it's greater than 5, if it happens to be greater than 5, there's no concern, right? Because that seems to be fine for the fish and all the other aquatic beings, right? And so we're only concerned if it's less than 5. Because we have the less than here, this makes it a one-sided test. And as you know now from assignment 4, you have to know if you have a one-sided or a two-sided test for your p-value, right? So we just kind of make a note that we have a one-sided test here, and then it doesn't come into play until step 3. But what I'm going to do here, I have it typed up in the notes, but just to emphasize, I'll just say we have a one-sided test. Because we're only concerned with one side. Any questions about that one? So, second step, do the test. Right here, we're going to calculate our t. It's going to be a t because in reading the question, right, we know our mean and our standard deviation came from our sample, right? And so we have a sigma unknown situation, and that's what makes it a t. Also, because that's the section that we're working in, right? But later on, say on test 2, right, you'll just have a bunch of questions, and it'll be your job to read those questions and determine what type of question you have, right? And that's going to be tricky, but I'll prepare you. Give you tons to practice on. So we calculate our t, right? Our sample mean is 4.771. Our hypothesized mean is 5, and our sample standard deviation is 0.9396, and our sample size is 15. So for this one, you can definitely check your calculations, right? But I've got them here. And we find a t to 3 decimal places is negative 0.944. So we've got this negative 0.944, which actually looks good because this is where we kind of check in and say, okay, where is this test going, right? What this is saying, because it's not very large in either direction, right? We already suspect that we are not going to reject the null hypothesis. Right? In our case, we didn't want to reject the null hypothesis because rejecting the null hypothesis means the aquatic life is at risk, right? So here we kind of breathe a sigh of relief and say, okay, it looks like 4.771 is not significantly less than 5, right? But we'll keep going because we have to have our p-value to back it up, right? But we do a little check-in here and say, okay, because that's not so far out into the tail, right? It's actually kind of close. We're probably not going to reject the null hypothesis, right? But let's keep going. So, got all these notes here. For writing out what you're doing to find the p-value, right? Step 3 is find the p-value. Calculated your t, negative 0.944. And so what you're going to do is you're going to write using the t-table, because you should always tell me what tools you're using. Using the t-table with degrees of freedom equal to n-1. And it's important that you tell me what degrees of freedom you're using, just because later on they're going to change, right? Or what if you're using the wrong ones? At least if you tell me which ones you're going to be using and you follow through, then I can give you more marks, right? Then if you don't tell me what you're doing, then I don't know what you're looking for what I'm looking at. So here I'm showing, okay, my degrees of freedom is 14. So then we find that we take the absolute value of t. Remember, the absolute value just has these two vertical lines around it. And that means we basically drop the negative. And so 0.944, if we go to our t table, is between those two values. So what we had was we had 14 degrees of freedom. I should scroll. 14. 14 degrees of freedom. And I've got my 0.944 that I want to place on this 14 degrees of freedom. And it's going to be between these two values, right? 0.868 and 1.076. Right? And so you're going to write those down just in case you did the wrong ones. Again, you're just showing all your work to show me that you know what you're doing, right? Even if you, I don't know, your eyes jump down the line, right? Then at least I can follow through and say, well, the idea was right? Little typos I don't take that many marks off for. So as long as you show me what you're doing and what you're thinking, you're going to keep a lot of marks, right? So 0.868, and that's what it's all about. And that's what it's all about. 0.868 and 1.076. We have to find our p-value. We have to check, do we have a one-sided or a two-sided test? In this case, we said we have a one-sided test because we only care about it being less than 5, right? And so our one-sided p-value is somewhere between 0.15 and 0.2. And so that's what you're going to write down as part of your answer. Okay. So here, it's going to end up looking like this. So when we're writing it out, what I do is I just put my calculated t in the center of the page. I start there, and then I write out the values that capture those, my calculated t, and then I put my one-sided value, the same idea, is between 0.15 and 0.2. Any questions about that step? No? Now for our conclusion. Remember, our conclusion has 3 parts. First part is we have to compare, how does our p-value compare to our alpha level? So here I'm saying, since our one-sided p-value is between 0.15 and 0.2, it is greater than our alpha of 0.05. Next step, what does that mean in terms of the null hypothesis? Which means we do not have enough evidence to reject H naught. Finally, our conclusion, we have to actually conclude it in terms of the question. Usually we get so bogged down in these questions, we forget this last part, right? There's a reason we were doing this in the first place. Therefore, we don't have enough evidence to conclude that the mean dissolved oxygen level in the stream is less than 5 milligrams per liter. Fish rejoice. I just want to highlight the different parts of our conclusion because it's going to be really important that we cover each of these 3 every time. Right? And so I'll use some colors here. Here's our first part, so where we compare our p-value to our alpha level. Call this part 1. I'll have to put it way down on the side here. Compare p-value to the alpha level. Alpha is just the Greek fish looking letter to the alpha level. So you have to tell me how they compare. Next part, part 2. Part 2 is your conclusion in terms of H naught, right? What does that mean in terms of your null hypothesis? Conclusion in terms of H naught. And then finally, the third part is your conclusion in terms of the question. Conclusion in terms of the question. Here's one thing to keep in mind. I usually make the conclusion worth 3 marks out of 7. That's a lot of marks, right? So typically a hypothesis testing question for me is 7 marks. 3 of those marks come from here. In theory, I've never had anyone do this, but in theory, you could skip step 2 to 3 if you don't know how to do it, and just say, I'm gonna assume that my p-value is this. Fair enough, you don't get marks for finding your p-value, but you could just say, here's what I'm assuming. I'm assuming I found a p-value of 0.0145. Just pick a random number that you know how to deal with. And then just state your conclusion beautifully in terms of that p-value that you made up. 3 marks in the bag. Pretty good. So in theory, all I'm looking for really, I mean, ideally you do the whole question, you know how to do it, right? But if you're stuck, I wouldn't hesitate to say, okay, I don't know how to find this value. It's not making sense, because recognizing that something doesn't make sense to you is good on its own, right? And so then you can say, here's what I found. It doesn't make sense. So here's what I'm going to use instead, right? And then just keep going, because the whole goal is to show me the things that you do know, right? And so if you can showcase that, okay, if I had a p-value, this is what I would do, that's worth something, right? And so that's what I want you to keep in mind when you're, well, writing tests in general, right? You want to get out there as much as you, everything that you know. Okay? So, any questions about that example? Okay. I have more time, just a little bit more time. I know it's, I know, cruel, but cruel and unusual. No, not that unusual. I'll just show you how we do it if we had to do it in R, right? Because steps 2 and 3, where we find the t and find the p-value, are really easy to do if we just do them in R. Okay. So what I've done here is I've entered the data that we were given in the table, okay, and I've called it DO, dissolved oxygen, arbitrarily. Okay. And how you do it when you have to enter your own data is C, so lowercase c, concatenate, and then brackets, and then in brackets, separated by commas, you have all your data values. Right, so that's what I've done here. Dissolved oxygen level is this data set. And then I can use the t.test command on dissolved oxygen level, because it's just one sample, right? How does it compare to a mu of 5, right? So I'm telling it, I'm hypothesizing that the mean is 5. Do that t-test for me, please. This alternative equals less is actually optional. It'll default to a 2-sided test, right? So that's why I had to change it to the alternative hypothesis is that mu is actually less than 5. But as far as the output goes, it'll look familiar, right? Because it finds this t of negative 0.94256. Let's see. Which is a little bit different from ours just because we were using rounded values. Right? But the t is very similar, degrees of freedom are the same, and it gives us a p-value of 0.1809. Right? we found our p-value to be between 0.15 and 0.2. Well, 0.1809 is between 0.15 and 0.2. So it's somewhere in there, and this is what it is specifically. It's just telling you what it's assuming the alternative hypothesis is. And one thing to keep in mind, if you want a confidence interval out of the t-dot test, you can't specify a one-sided alternative. Because for some reason, I'm sure there's a good reason for it, I just don't know it, it'll only give you one of the bounds. Right? So you have to have not equal to, so the default, right, is just a two-sided test to get both sides of the confidence interval, but that's just if you wanted it. And then here's the mean of x, which is, we were using 4.771, but it's actually 4.771. 3 repeating, presumably. Okay. Over on the side, for a lot of the questions that we'll be doing, I'll only give you the mean, so the sample mean, the sample standard deviation, the sample size, and the hypothesized mean. But what we can do is, well, here's the mean, the sample standard deviation, the hypothesized mean, and the sample size. So what we can do, if you wanted to check your answers, you can calculate a T, I just called it T dissolved oxygen, to name it something other than T because T is reserved. Sample mean minus the hypothesized mean over the square, the sample size, the standard deviation over the square root of the sample size. And then we can use the PT command, which takes a T value and the number of degrees of freedom, and it gives you the one-sided p-value. Okay. If you wanted the two-sided p-value, you can just multiply by 2. There you have it. So, any questions? So we'll start with the written example next day. Make sure you get assignment 4 in. Still got one copy of chapter 5 notes if you didn't get them, but I think we're all good. See you on Wednesday. Assignment, I do. Yeah. Got it. Oh yeah.